So we started looking at an idea that was originally proposed in 1961. Again, I keep coming back to 1961, a very important year. It's the year that Yuri Gagarin did the first human flight in space. It's the year that Frank Drake began looking for aliens, and it was also the year that a very visionary scientist, Robert Forward, proposed using lasers for light sailing. His point was a laser could focus light a lot higher levels of power, and that you potentially could use light from a laser to push a spacecraft to speeds that could get you interstellar distances, maybe 10–20% the speed of light, that would allow that journey to take place in a few decades. Although when Dr. Forward made these proposals, the laser would have to be the size of the Earth, and the power would be immense to send a spacecraft of the capability that we thought we would need in the 1960s. Although there's been a lot of work since then, and this is really what we're basing our Starshot effort on. There was a very capable scientist from the University of California at Santa Barbara, Philip Lubin, who, under the sponsorship of the NASA Innovative and Advanced Concepts program, said, look, over the last few decades, we've made a lot of progress since Robert Forward made a suggestion. Professor Lubin said, first of all, spacecraft are getting much smaller, and I'll talk a little bit about how small they can go. And second, the ability to make much more powerful lasers much more compactly has increased, largely due to developments in photonics, the ability to use light for communications. So the idea that Professor Lubin came up with was that if we could build a very, very powerful laser, and a very big laser, but certainly less than the size of the Earth, but maybe a kilometer in diameter, that could produce levels of power that, to be sure, are maybe 1,000 times more than we can produce today, like 50 to 100 gigawatts of power, where we could produce megawatts of laser power today. Then we could potentially have enough power to propel a spacecraft to some fraction of the speed of light. Now, the second thing, of course, is that the spacecraft has to be very, very small. So the second thing is, can we make spacecraft of a gram size? Now, one of the key questions, of course, is that this sounds like a really huge laser, and it is. Can you produce this thing affordably? And we could calculate that today, in 2017, we could probably build a laser this big, but it would cost trillions of dollars or trillions of euros. However, that Professor Lubin pointed out that the cost of lasers is decreasing every year by about a factor of 2. This is the well-known Moore's law for electronics, but it also holds for lasers. Also, the cost of lasers of particular power is decreasing, allowing the power to increase again by a factor of 2. This suggests, if this trend continues, and we have every reason to believe that it will, that within about 10 or 15 years, we will be at the level where a 100 gigawatt class laser, which we call a light beamer, could be feasible for about the cost of large science projects today, like the James Webb Space Telescope or the Large Hadron Collider at CERN in Switzerland. So this is really an interesting possibility. Now, again, as I mentioned, the second thing is the spacecraft has to be really small. Now, today, a spacecraft is like a communication satellite, weighs thousands of kilograms. So if you look at the calculations that Philip Lubin did, this is impossible to get to 20% the speed of light. However, we're seeing a huge decrease in the size of spacecraft. Today, we can do most of the things we do on a spacecraft that weighed 1,000 kilograms a few decades ago with a kilogram class satellite. Again, we keep coming back to this factor of 1,000. Can we make a spacecraft a factor of 1,000 times smaller? Now, this is an interesting question. Although if you look at what a spacecraft actually does, much of those functions, the computer functions, the memory, the sensors, and so on, are contained in, for example, an Apple Watch chip, so a chip you have in your watch. But can we make a spacecraft out of it? And so this was a key question. Can you make a gram spacecraft that does everything a normal spacecraft did? So we actually did some development and looked at this and found a group at the University of Cornell that has been developing what they call nanocraft, and they built a prototype for us. This is a prototype of what we call a star chip, and it weighs about 1/3 of a gram, and it has on it essentially everything that an interstellar spacecraft would need. It has computer memory, it has cameras that can take images, it has a laser that it can beam the light back to the Earth, and it has 4 small lasers so it can orient. It has power. It would have a radioactive battery, or there may be other means to do this. So the idea that we could do a star chip is very interesting. Indeed, on 23rd of June of 2017, this year, a earlier version of this star chip called Sprite, the Sprite nanosat, which was built by a number of young researchers at Cornell University, was launched on the Venta satellite, which was Latvia's first satellite, and demonstrated that it could work. So we're making very, very good progress on star chips. So the idea is you take this star chip and you connect it to a light sail, an ultralight, highly reflective material. You then use a laser to push against it for a few minutes. These star chips and the light sails would be held, maybe 1,000 of them, on a mothership orbiting in a direction that you want to go, and we've chosen the nearest star system, Alpha Centauri, is our target. The laser then hits it for a few minutes and accelerates it at very, very high acceleration, like 60,000 gravities towards Alpha Centauri. Now, this is hard. In fact, this is really, really hard. We've listed about 25 major challenges. Of course, the first one is the laser array, the beamer. Can we build these things affordably? Can we build a kilometer-size laser? The second main thing is the sail, the light sail. Can you build a light sail light enough with the material properties so that when you hit it with all this energy, it doesn't just vaporize, but it actually pushes in an even manner to go the direction you want. So the light sail is a second major effort. The third one is, can you really communicate back? As I said, we have a small laser on board this chip, but can we focus it back on the Earth with enough accuracy that you can actually get a real signal? Now, theoretically, we calculated that you can. You can use the sail itself or deploy a small telescope or optical element after you fly through your target system, and then aim that back at the Earth. And then you can use the transmit array. Remember I said it's a kilometer laser, as a receiver, as a giant telescope. And we calculate if we can do that, we can communicate back from the nearest star system, Alpha Centauri, which is about 4.3 light years away. Again, this is about 300,000 times further away than the Earth is from the Sun. There are, to be sure, policy issues. This much power beamed into space, we have to make sure we don't hit somebody's spacecraft, so there's a lot of key policy issues. But we think now is the time to start. So the breakthrough initiatives, through Mr. Milner's funding, he committed $100 million over the next 5 to 7 years to do research on 3 of the critical efforts, which I'll mention in a moment. And then if we're successful, we would then, in about 5 to 7 years, begin building a prototype. It wouldn't be the full kilometer laser beamer, but it may be a 50 to 100 meter beamer. We wouldn't be able to get the star chips to 20% the speed of light, but we may be able to get them to a few tenths of percent the speed of light. So that would be privately funded, we believe, as the initial research. Probably cost about $1 billion US. But then if that worked, maybe about 20 years from now, we would start building the full-scale interstellar system. This would be probably too much money for the private sector to fully fund, but we could do this in partnership with governments, that this would cost about, again, maybe of order $10 billion or euros. So this is our plan. We have an advisory committee of distinguished scientists, including Nobel and Breakthrough Prize winners, key people that have done a lot of work on the various component technologies in the science. They meet every 6 months to review our progress. Now, we've made a lot of progress recently on this. Just in September, we announced the request for opportunities for the initial phase of laser development. We expect to have 7 or 8 contracts on contract by January, February of 2017. Here in October of 2017, we will soon have a similar effort for the sail development, and then for the communications technology early in 2018. So we can begin doing our research very, very soon that has huge potential to actually get humans interstellar distances.